Maybe leave one window to survive a little bit with fresh air. Okay, all alive from yesterday's. Okay, I am also tired, so it will be a little bit slower the pace today, but it should be good enough to just finish what we started yesterday, yes? So yesterday I started building everything we need in order to learn cyberwritten theory. And okay, super quick recap, like super quick. We are looking at the simplest possible case because that's how much time we have. We are looking at pure n equal to 2 super young males with SU2 gauge group, and that's it. Nothing more than that. And the first thing we said, or one of the important things we said, is that we are going to give a VEV to the scalar. And with this VEV, we will break SU2 down to U1. This is allowed, it keeps a supersymmetric vacuum because the D term is 0, yes? All of this should be clear. So one tiny little comment that I wanted to make yesterday, and I was super fast and I even forgot to say this, is that even classically, let's just look classically, there is this A going to A. This is gauge equivalent, yes? So this I don't want to have, so I need to define a gauge invariant quantity. So this will be U is equal to A squared. By the way, between all the different reviews, there are gonna be factors of half there, but anyway, like I don't want factors, I'm tired of them, so it's like this. Yes? And this is also very physical. This U is the vacuum expectation value of trace phi squared, the gauge invariant operator. Yes? And this is correct classically. So in the super weak coupling, basically coupling to 0, and quantum mechanically, you will get corrections with respect to the coupling. Yes? And in some sense, this is the name of the game. We need to find a way to compute all of these corrections to all orders. That's what we are doing. Are there any questions? So now I am not going to be able to know if you are just broken from tiredness or you don't understand anything. So please try to be responsive a little bit. So we start from the UV, we give this VEV, yes? We let the theory flow to the IR, yes? All the massive guys are integrated out, and we are computing the effective Lagrangian. I remind also this. So we have this holomorphic prepotential, and we will use complex analysis to determine this beautiful function. Super quick reminder also for the second line. I'm not going to go to components, but just the super field. Yes. And from here, okay, I'm not going to write the components. This is where we get tau IR. And from here, so there is a derivative here. This is where we get the metric on this scalar target space. So this is what we are doing. And I finished like the last bit yesterday by writing how we are going to go to dual coordinates. So this is the rule, if you wish. And in some sense, if you imagine in your head for a second that this is n equal to 2 superfields, just by plugging in here, you see the duality immediately in your mind. Yes? And what I said, oh, this is nice, because what can I do with it? First of all, I can write what is the IR coupling constant. And this is this. And I can also write it in this way. Yes, simply from here. And then I can also do a tiny computation to make sure that I'm doing what I want. So I can take the second derivative now of the dual prepotential. And from this, which gives me that the dual tau went precisely to this S value. So we are with this change of A's to AD, we do precisely what we want to do. Yes, this is very good. This is an S transformation. Now, what I am not going to do because of time is, basically there are two very, very important things. One is that this change of variables is in fact, it leaves the path integral invariant. And two, it also leaves the spectrum of dions. So the path integral, I'm not going to do it. I am just going to write it. I mean, very stupidly, in n equal to 2 language, you can immediately see this. You can write, using this equation there, you can write that this is psi-psi dual. So, of course, if you go from psi to psi dual, this is going to stay. Now, in this n equal to 1 language, Bilal has it, and it's like a page, but you can very easily check that this is the case, and maybe also looking at this one is almost immediate just by having this equation there. Yes? And you can also check in Matteo Bertolini, he does it with components. Yes? So the point is that the path integral, if you change from the original to the dual fields, while changing tau to 1 over tau with a minus, the path integral remains the same. Yes? So this is the first very important thing. And by the way, remember that this is the S part. We also have the T part, which is shifting the theta by 2 pi. And this is the symmetry of the path integral anyway. So we have the full SL to Z, yes? So this is very important point, maybe let's like number 1. And the second is the spectrum of dions. Let me do this super quickly. So first of all, recall what we were writing, that the mass, this is the BPS bound, right? So we were writing this, and this is A. This was one of the forms in which I brought it, which looked really nice. Here is super easy to see what happens under an S. I will do an S transformation, n comma m will go to m comma minus n, and A will go to AD now, yes? AD is right there, is F prime, but in the weak coupling, F is tau in the UV, A squared. So this is nothing but, okay, and there should be a half here. This is this, in the weak coupling, which for now is all we know, we don't know more than that. So you can take this equation, and M is going to go to what? Is going to go to AD M comma plus. Yes? Plug in for AD, so this is this. Tau A, multiply inside, you get N. It stays the same. Yes? So this is this statement. This transformation also leave the spectrum of Dion's invariant. Of course, what I just did is that I used the weak coupling, but this is all I know at this stage. We don't know the full solution yet, yes? So, but with all the evidence that we have, it looks like this is the case. Fantastic. So now, we are really ready to go. One tiny reminder from yesterday, and we are really on shape. Yesterday, I wrote down the one-loop Coleman-Weinberg calculation, and I just write now the answer. So this is our friend, and I want to use these equations. So we all know how to take derivatives. So this is the answer. Please check me. It's a hard day today. So this is what happens when you take derivatives. And maybe I write here, these formulas, they came from a one-loop Coleman-Weinberg calculations. These are valid in the weak coupling regime. Or in other words, I will write these words here. These are valid And in this regime, we will also see this in the very end when we will have the final answer, is the regime in which you can drop all the instantons and you get back to this beautiful formula. So whatever I will derive today, in the end we can expand it in this regime and we will get this formula. This is very important, and this way actually I will also fix the normalization of the solution. So now this is amazing. So this is the only thing we have. We have this map there, and we have the beautiful thing that we learned also from the first week, that whenever something massless happens, whenever someone becomes massless, oh, there is some singularity going on. Yes, this you will never forget, I think. So now I will do the U-plane. So, and we also said that we need to use this U coordinate because this is the gauge invariant guy, right? So the solution of the problem will happen at the U-plane. And this will be the coordinate that I will use to describe my Coulomb branch, yes? And first we begin in the weak coupling. So you can say G to 0, or this is also because of what I wrote there, U to infinity. This is this regime. Very naively, classically, the U-plane is just the complex plane. But of course, things is going to happen in this life. So we are in this weak coupling regime. So we are basically very, very far away from the origin. By the way, this is like the example that I gave, that when you were going to 0, something was blowing up in your face. So this is going to be the strong coupling. And for a second, let's stay away from this region, yes? So now, okay, I will try to use colors. So now we will be here. Yes, at infinity. So these equations are correct very far away, at infinity. Yes, and to do what I want to do, I will write these equations with U. I will write like this. A of U around infinity, it looks like this, yes? And AD of U, because these are my two players, these are the two coordinates that I'm going to use to describe this madness. Again, around infinity. Please check my... I'm trying to be very careful, but... Yes, so these are my two things with which I start with. Yes, I just plugged in. Now what do? Now we will take around, we will go around in a counterclockwise way. We will make a whole circle, yes? So take okay, English is going to disintegrate. And we will do this around the point where we know what is going on, which is this, around U infinity. If you wish, you can even think that you take the plane and you make it to the sphere and you go to the other pole, yes? And around that, we understand what we are doing. And we will go U to U, 2 pi I, a full rotation, yes? So what happens to these guys when we do this? Let's just write the answer. So A, because of the square root, will go, yes? And this is minus A. So A goes to minus A, yes? And then AD is going to go to, okay, there are some factors, minus A, ln here. Maybe I send it upstairs. And I continue below it. Yes? What is this? Oh, this thing I can write in a nice way now. I can write it like this. There is a matrix. And this matrix at infinity is this. And also maybe note that this matrix can be written like this. T is this shift by 2 pi of the theta, and this is an SL2Z matrix. Yes? So what are we discovering? We have these two types of coordinates, the original and the dual. And by making a contour around the infinity, the point that we know, we discovered that these two guys, they are not, holomorphic. They actually have some singularity, some branch that is coming out of them. Yes? So let me write. So there is a non-trivial monodromy. So this means that these functions AD and A are multi-valued. I will also write, there is a branch cut coming out of infinity, yes? And this branch cut, it has to go somewhere, right? It really has to go somewhere. So we actually, this is like part of the job that we need to do. We need to find where this branch cut is going to go, yes? Maybe I just go here. So this means, and this is how we will start discovering what this U-plane is, because now we only know infinity. We are very, know nothing. Yes? This means there must be other singular points on the U-plane. Yes, because the branch cut has to go there. And very stupidly, if we don't know anything else other than what I said, this is the U-plane. We just did this big monodromy around infinity. There are going to be, I don't know how many. Yes, so there is going to be an equation like this. Let's call it U1, dot, 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 UK. These are all my singular points. And at this stage, we do not know how many they are. So, how many this is the question we need to answer. Yes? Okay, let's answer it. To answer it, we need a tiny little bit of physics to go in. And I have already covered this physics, so this is really great. So, the first thing to answer this question is we need to recall that the n equal to 2 vector multiplet, and in particular phi, has this U1R symmetry. Yes? That's very good. And in fact, okay, we really didn't, this is really just classical. And the point is, and I'm not going to cover it because there is really no time, when you go quantum and you take in account all your quantum effects, this symmetry is going to break down to a Z4. But I don't really even care about this. I only care on how it acts on the U plane. So this I just tell you, just to save time. We have a Z2. So we have a U going to minus U. This is the leftover of so please, this, you just have to believe me. That's all there is and nothing else. Yes, and we can look at this in the final answer. It will be there. Now, this, it means one thing, that if I have all of these singularities, they always have to come in pairs. So if I have a U, I also have minus UI. There is no way out of that. Yes, of course, this does not hold for U infinity, which is what we did, and also, and possibly, for U to 0, because also this doesn't have its unique. Yes? Other than that, everyone else should come in pairs. Yes, the singular points. I mean, the complex plane is nothing. The complex plane is a very nice plane that nothing happens, and the only thing that exists is the singular points. Nothing else happens on this thing. So it's topology question, it's not even geometry question.
But I don't understand why we know that we can only have, why we cannot only have infinity or 0. Why that has to be.
So we cannot only have infinity, because if you shoot a branch cut for a point, it has to go somewhere. So there is no branch cut that doesn't go anywhere. This is not possible. So the minimum solution, which I will discuss now, is you start with a cut from infinity and it goes to 0. This is the most simple possibility. Let's discuss this. Or, of course, it can be something way more crazy, yes? So at this stage, we don't know anything else. We just know that these are the options, yes? So the simplest option I will write possibility, because it's not gonna be the case. It's just not going to be the case, is that we have only U to infinity and U to 0, singular points. No one else. Yes? Let's see why this is bad. This is very simple. So if this is the case, this means that the coordinates A of U, or U of whatever, this A, is a very good coordinate, starting from infinity, where it's a good coordinate because it's a weak coupling, all the way to 0. Let me tell you now why this cannot be. We have learned that f of A is holomorphic. Yes? And we have also learned that the metric G phi phi, which is the imaginary part of tau Yes? This is a harmonic function. But what harmonic functions do? Harmonic functions oscillate. Eh? But if this oscillates, this is not going to be positive. We said this, that it has to be positive definite to be a good metric. So in this case, that I am allowed to use A all the way from infinity to 0, even if you exclude the tiny region around 0, but still all the way, there is a contradiction here. So this is not allowed. We basically need things to break down faster than 0, closer to, yes, please. If this was a good coordinate, because we are trying to describe the complex plane, right? So everything is good and perfect if you are not at 0. So at infinity, we know that A is a good coordinate because this is how we started describing the weak coupling. So the only thing that can happen and break down is at 0. And all of these functions that I am writing, they should be well-behaved functions everywhere, apart from 0. Yes? But A is holomorphic. This is harmonic. It has to be a good metric. By the way, there is one solution to these restrictions, and this solution is that the constant function. The constant function is a perfect solution, but not for n equal to 2 theories that they have a non-zero beta function. It could be a perfect solution for n equal to 4 super young mills. Yes, but we are doing something a little bit more advanced now. So this is out. Maybe I write this. Okay, sorry, this is super fast, but I think it's clear what I just wrote here. For n equal to 4 super young mills, that the beta function is 0, this is acceptable, not for us, where we have a non-zero beta function. Yes, ask.
So before we start doing all this, we knew that there was a singularity in U equals to 0 or A.
No, we didn't know anything. We only knew what happens at infinity, at the weak coupling. Other than that, we don't know anything. How do we know? The only thing we know in this life is, for now at least, weak coupling, nothing else. I didn't say anything else. And now I am discovering, by the power of physics, what can happen in the rest of the complex plane. And this is just physics.
But isn't A equals to 0 integrating out everything, so...
A is equal to 0 is very bad in this life, and this is why I gave this example in the first week, the last lecture, 5th lecture. I had the phi1, phi2 example. When you send your VII to 0, whatever you thought is massive, oh, it became massless, it will blow up in your face. Yes?
So this problem still stays, like in the U plane?
No, this is a problem that was correct. So what you are thinking is correct for this stupid little example that I gave back then. But now we have instantons, we have many non-perturbative. I don't even know what is happening, and there is no reason to assume. Like, there will be crazy corrections that I have no idea how they will come about. So I have no idea. No one should have any idea, at this stage at least. Yes? So, what we know now is we have one singularity. We definitely don't have two. So what is the next simplest case? 3. Yes? okay, I will go with this, and I will solve the problem with this, and it turns out that this is the right thing, but I have to say, people wrote papers about this. So, this is the minimal way to find the solution, and then you can go and argue with yourself, is this the only way to do this? Yes? Yes. So I will just say, this turns out to be but again, people after the Cyber-Witten papers wrote papers on this. So it's not a stupid question to try to ask, is this really true? Yes? And if we go with the number 3, we are going to have an equation like this. So we will have our beautiful monodromy at infinity, some point that I don't know where it is, I just call it U0. And because we set this thing with the R symmetry, there will be the minus friend. And that's all we know. So let's go with that now. Yes? Okay, here comes, again, if you wish, another magical moment, but also this is why I did this example with the phi1, phi2, that when you see something blowing up, you say, oh, someone became massless. So what are we doing? I said also from the beginning that we want to use electromagnetic duality, and that's why we introduce also this AD gadget. Yes, if we have electromagnetic duality, we have also all of this dion spectrum, and we know that there will be points in which, for example, any dion, or let's just say even simply the monopole, will become massless, right? So let's use this. Yes? So this is really just physics intuition. So I mean, we know that this will happen at some point in this life. Let's discover when this happens. We know actually very well when this happens. And this is, we wrote this equation a billion times. I don't need to write all of this. And I wrote it also in this very beautiful way. So for the magnetic monopole, this is just AD, right? So the magnetic monopole becomes massless when AD goes to 0. Yes? As simple as that. So now I am gonna look for something happening, yes, because this is what we said, someone becomes massless, singular point. I'm gonna look for something happening here. And I will actually, just to go quick, I will first write for you the answer, and then I will derive it for you, or argue better, because it's not a mathematical full-on derivation. So how can I make this possible? I can make this like this. Let's write AD is equal to some unknown constant that at this moment I have no idea. Yes? Sorry, this equation is annoying me here. I will write it here. Yeah, this is what we are doing, the monopole. So something like this should happen. I will derive this though for you. And then there will be also something like this, which again I will also derive. Oops, what happened? Something like this. But this is consistent with what we are saying. The magnetic monopole becomes massless. So what happens if I go with this? Let's go with it. I derive the monodromy. By the way, there is also this annoying constant that I wrote C naught. There is no way to fix this constant. So but it always cancels. Rescale it. And where I'm going to rescale it, there is only one scale that I have in my problem, which is lambda. Yeah, so let's just rescale it so that this guy goes to this guy, squared. Just rescale it. So if we go with this, now we will do a monodromy. Again, anticlockwise around u is equal to u naught, which now we rescaled it to be lambda squared. So this is what I'm doing. I'm doing this transformation. And I will just write the answer. So I take this equation, which I will derive for you in a second, but I will just write the answer. This is what I get. And this will be, by definition, my monodromy matrix. And my beautiful matrix is like this. Is like this. And you can also write it how I wrote before in terms of SL2C matrices. This can be written like this. Yes? I keep this. I go there. Is this clear up to now? Any complaints? So why on because before I say this matrix that I just wrote there has a magical property, and I will just tell it to you now. And if you want, you can make me more calculate this in the Q&A. This matrix, when you act with this on a monopole, it leaves it invariant. I think this is enough. This matrix with the 1, 0, minus 2, 1, when you act on Mn, it leaves it invariant. Yes? Maybe I just write this. If you remember what I had done, I had defined that Z can very beautifully be written as MAD plus NA, which you can think as MN dotted with this. Yes? So, of course, this matrix acts on these babies, but you can also think that it acts on these babies. And when you choose 1, 0, and you act with this from this direction, it leaves it invariant. You will get back 1, 0. Perfect. Okay, so now I will just say what is the third monodromy, and then I will derive these equations for you. So the third monodromy around, so the minus u naught will be minus lambda squared now. Yes? I just do it by Cauchy. So we have this equation, right? Yeah. This is like this. And if you also want to write it with T and S, you can write it like this. And this is nice because you can also write it as T Yes? So this looks like a similarity transformation on the plus lambda squared matrix, which is very nice because this reflects this Z2 symmetry that we had on the U-plane. Yes? I'll just write nice. This. I mean, nice means makes physical sense. Yes? Nice. This reflects. How are we doing? Yes? Everyone alive and with me? Yes, there is no argument in some sense. The only argument is that there is no 2. And the next simplest case is 3. So we just go with it. We go with it, we will solve the problem. The solution will look nice and we will say, maybe this is good. But what I said is that people wrote papers and it's not 5, it's not 7, it's not that, it's 3. And this is not something I can actually tell you. So, yeah, you can spend some years from your life studying all the cases and at some point believe. And okay, let's also say the following. You can actually really say that Seiberg and Witten theory is not a mathematical theory, it's a beautiful patchwork of physics arguments. And if you wish, we are confident that this is really correct, also because Nekrasov derived his Nekrasov partition function and can derive also this from a localization from a UV principle. Yes? So Seiberg-Witten theory is really a collection of physics arguments. And always in physics, the simplest cases, like I have never seen that, how many singularities, 132. I've never seen something like that. Yes, but anyway, this is just beauty. It's nothing. So let's derive this baby. How do we derive it? It's super simple, actually. We will really go all the way with the electromagnetic duality. What does this mean? We will really go to the point where the monopole is massless. This is a strong coupling regime. So this is this. But, and that's why we do this as duality, but for the A dual coordinates, This is weak coupling. And what does it mean if in the original coordinates I have a massless monopole? What is this in the dual coordinates? Well, I will have some electron, some dual electron. Of course, weakly coupled to the n equal to 2 photon. A dual n equal to 2 photon. Yes? But if you accept this, I can write to you the answer. Yes? This, a photon with an electron, is called QED. We know how to do it. Okay, it's just n equal to 2 QED. This is n equal to 2 super QED. Yes? And I can do everything for that. And in particular, I can calculate its beta function. Okay, I will just write the answer clearly. I'm not gonna even try to calculate. There is no time. But this is something you all know super well from your QFT. And I think also the pi's and everybody is correct. Yes? So this is n equal to 2 super QED. N equal to 2 is important because the precise factors here are the precise counting of all the degrees of freedom, yes? And now we are in business. Okay, we will define our tau coupling, the tau dual, to be, we are doing super QED, so there is no theta, so there is some baby like this. And also what I do, because we are doing an effective theory, we will take the mu, the scale, to be AD, the scale of the theory. That's all we know nothing else. So we take this to be that, and this is our tau, our holomorphic coupling. And now we write things out. Wait, I will put this a little bit here, maybe. Yes? And now just okay, here I'm using the beautiful equation that I wrote, the magic of Seiberg and Witten, yes? And, oh, look at this, I just derived the one equation I promised. This equation is this equation, yes? And there is only one thing missing. This. Is it okay? Yes. Because we are studying effective field theory, and we always choose the scale in which we do our experiment to be the only energy scale we have in the problem. And in this case, the only energy scale we have is this AD. We are in the dual description, so we only can use the dual coordinates. So that's the only gadget we have, nothing else. These are important questions. Yes, please ask if you have such things. So here I haven't done anything. Okay, I wrote down the answer for you. You should be able also to believe it. It should be more or less clear up to an overall coefficient, which always, also in the end, it doesn't really change anything. Yes, so here I did all of the manipulations, hopefully correctly. This equation was already written in the blackboard. Yes, and I just use it, and out of it I came up with this equation, which is the second equation that I told you I will derive for you. Are we happy? Yes? So there is one tiny last thing, and I have derived this full on, and this is the following. So we know that near u0, yes, this AD is some function of u that we don't know, but we know that it has to go to 0. Yes? Because this is how we started, because this is the point in which the magnetic monopole becomes massless. Yes? So we know this. So in principle, we could write, and we only care about a patch near u0. We don't care about, like, we are really local now. So we know that AD, it really locally, it has to be something like this. It cannot be anything else. With P positive, by the way, a positive power, otherwise we would have problems, yes? Do you all agree with me? So the only thing that I'm not telling you, and I will tell you now in a second how to fix this, and then you have this equation perfect, is what is P. So P you fix with demanding. You can say it in many ways, but basically demanding that everything is compatible with SL to Z. Because this is part of our assumption, right? All of these dions that we have, they all transform beautifully like this. This is like, without this we have nothing. So what does this mean? That whatever matrix I derive from whatever stuff I write here, you should be able to always write it as an SL to Z matrix. And I claim that if you do that, P becomes 1. And then you have this equation in the box. Is everyone happy with this? Amazing. You want to ask something? So, this is as far as a human being can go with physics. Yes, that's as far as you go. And we went all the way. We used all the, smart things, all the assumptions, all the singularity, or someone is massless. We used it all. And now we basically have a mathematical problem that we need to learn how to solve. So from now on, it will be just that. So let me write this. Now, so what is this math problem that we have to solve? So we have on the u-plane two functions, AD of u and A of u. These functions are single-valued everywhere apart from 3 points. Yes? And we know the monodromy matrices that mix them up around these 3 points. This problem is a very well-known mathematical problem, and it has a unique solution. And I will try to explain this to you now. Maybe I just write. So when I say that these are single-valued except, it means that they are multi-valued. Just to stress the language. By the way, when I say well-known math problem, I didn't take a math class where they taught me this. I had to learn this by myself. I don't know, if someone has taken a math class, they should really bring chocolate to this teacher. Because there is really no way, in the first complex analysis course, there is basically no way you ever cover this. You would cover it if you take complex analysis 2 or something. But I think we never take such a course, as physicists at least. And I think the mathematicians don't do it because it's too concrete for them. Yes. Yes. But if you, so the way I bought books on advanced complex analysis, yes? So this is how you discover this. So this is called the Riemann-Hilbert problem. This. So we have, okay, let's repeat the problem. We have two functions that they live on the u-plane, and they are good, they are holomorphic, apart from 3 points. And in these 3 points, we know the monodromy matrices, which is the ones we derived, that tells you how they get mixed. This is the problem. And the problem is, given that, write down the exact solution A of u and AD of u. That's the math problem. That's a very concrete math problem. And when I will write the solution, you will look at it and you will say, oh, yes, this is what it is. Yes, but now, yes. And what is important? This is very important, the uniqueness. And maybe I say another thing. Of course, Seiberg and Witten knew about this mathematics because these mathematics appear, at least up to before them, in two places. So people that study integrable models, they knew this. And people that studied 2D CFTs and blocks knew these things. So people have been doing these things. It didn't came out of the sky. So they have been really doing precisely this thing. And very practically, very practically, if you want to calculate, again, not be a mathematician, there are two, if you wish, distinct ways to study this problem. One way is to study, so these A and AD, you can think of them as solutions of differential equation, which basically is something like a how is this? Yes, say? Quantum mechanics, how is it called? Quantum mechanics. What is the equation? Schrödinger. So it looks like Schrödinger equation, yes? It just has regular singular points, yes? So this is the one way to approach this problem, very concrete, and you do it. And by the way, this very nice review by Adel Bilal, this is how, so they phrase the problem up to this, and then they go to this differential equations language, because everybody knows quantum mechanics, and they solve it like that. Yes? Cyber-Witten, what they did is another, both of the ways, they are the same thing in the very end of the day, but the very pragmatic way you do the calculation looks different. And the way the Cyber-Witten did it, and we will do the same, is that they said, oh, there is an auxiliary spectral curve, out of which we will pull out the solution like a rabbit from the hat. And this is what we will do. Okay, I can just write this. Practically, yes, and when I say practically, I really mean calculationally, all the way to equations. One is A and AD are solutions to this in a more general way. It was known in the integrable people as Picard-Fuchs equations. But anyway, this is a stupid name. It doesn't mean anything. It's some differential equation, yes? And you are physicists. When I give you differential equation, you know what to do. So in some sense, what Bilal does in his review is amazing. It's very clear, very beautiful, yes? And then the second way, we will pull out this A and AD as periods integrals around cycles of some auxiliary curve. And this is what is called the Seiberg-Witten curve. Yes? And maybe I just say one thing because it's nice. This auxiliary curve, when Seiberg and Witten wrote their paper, it's like a magical thing. Why does it even exist? But this auxiliary curve actually is really real in string theory. So in string theory, it's a brain that has a funny shape. And you can calculate it. And actually, after the original Seiberg-Witten papers, there was a paper by Witten alone, I want to say 97, yes, where he in fact calculated this by these Hanani-Witten constructions. Anyway, this is for the people that care about that. So it's not an auxiliary, imaginary, whatever curve in our imagination. It's actually very real if you know string theory. And it's very easy to really write it down if you know. So string theory knows everything also. This is very nice. Okay, just a little bit to remove maybe a little bit of fear before I start writing crazy things down. A very typical example of such a solution of such a problem, you know if you have ever studied hypergeometric functions. And in fact, the solution to our problem will be a hypergeometric function. So, so let's write, we have a function. So now this f, because I don't want to write this annoying indices all the time, this is the 2, 1 hypergeometric. And for us, all we need to know in this life is the integral representation of it. Okay, there are some annoying factors in the front, but it's fine. Here is the integral from 0 to 1. Maybe one person can open Wikipedia and check me. No, I am being careful, I think. And by the way, this is important that so this is the integral representation of hypergeometric function. Now, everything is in the integral, and you can look at it with your eyes. This integral, you can clearly see there are 3 singular points. The 0, the 1, and the infinity. And you can take the u around this c. And what is going to happen is that your beautiful function f is going to mix with something very similar. Let's call it g of u. Now, this is precisely the point, that you will get another power of u. This has to do with boundary conditions, blah, 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 blah. And some other hypergeometric, I mean, which is the same family, but you know, these coefficients will a little bit get twigged. So now this problem is not completely unfamiliar, no? So this is the problem I'm going to try to pull out now of the auxiliary curve. We have two functions, and this is where we are going. Our solution for A and AD will be an F and a G. And I only need to tell you precisely what these powers are and precisely what these ABCDs are. That's all that there is going to be. So this is very familiar now, yes? There was some mathematical physics course where you did something like that, yes? Maybe they didn't call it what we want to call it, but this is what it is. Okay, now I will first describe the auxiliary curve for you in a language. I will try to do it as nice as I can, and then I will connect it to this. Yes? So let me write an equation first. So this is the Cyber-Witten curve for pure as U2. And maybe I will write here a little bit, you know, just for us. If you want to describe generically such a curve, in case it's not obvious, so this is the more general way to describe it. So from here to here, there was a choice for what is E1, E2, E3, and more importantly, E4 is infinity. Yes? And then I can write this. So this equation describes a torus. And let's try to understand this. How do I understand this? Let's be very baby, it's very easy. So first, we have y is equal to plus minus the square root of this stuff. Yes? So if you have that, this tells you that you have two seats. So I draw this, and I draw this. Do you accept? So this is the y is equal to plus, let's say, and this is the y is equal to minus. Everyone happy? Okay, so we have two seats. Now, on each of them, there will be so-called branch points, which you get when you look for the zeros of this gadget. And this is also why I wrote this more complete thing. In fact, there will be 4 branch points, yes? So, I hope this is super visual. Four of them. And I just, okay, maybe I should make it a little bit bigger so that I can make a nice picture. So I just put them. So here, let's say, is minus lambda squared plus u and infinity. And of course, they're friends correspondingly down here. Yes? So now it is my choice how I draw my branch cuts. I write this. I just do this. Yes? And when you have your cut, you follow all your way down to the next. See? And if you are here and you hit a cut, you go up. Yes? And by the way, why this is clearly a torus? Topology class 101. So you think that the plane is a sphere, you put the infinity point and you make a sphere. You have another sphere. The cuts are tubes. And this is your torus, yes? So is it completely 100,000% clear? So here is our torus. And amazing. Okay, maybe I just write this for everyone. So now we are interested, because we have these monodromies, in the points in which the torus degenerates. In this picture, I will just now draw, we will say that we have cycles, and these cycles shrink, and then our torus degenerates or pinch, yes? And let's try to use some color. No, green is not gonna do it. Red and blue, maybe. I mean, I can also draw it there, but anyway, it doesn't matter. So this is not red. This is the A cycle. And of course, this is topologically equivalent with this. Yes? Yes? And this is the B cycle. Now green or blue, what is this? Blue. Is this visible or I made it worse? So our torus degenerates when certain cycles degenerate, which means that we have zeros that collide. So let's do very explicitly. So when U is equal to lambda squared, what happens? We can look from the picture. The B cycle shrinks, yes? And this is the point where our magnetic monopole becomes massless, yes? Mono. This is the physics of that, but we are going there. For now, I'm just doing math. If I take, let's look at the A cycle, the option on the right, U to go to infinity, then the so-called A cycle will shrink. Yes? And this is the weak coupling. Or we want to match it with the weak coupling eventually. Yes? And of course, there is another choice that u will go to minus lambda squared. And this is a linear combination of A and B cycles shrinking. And this will be the dione. Is this okay? Visually, very visual? And of course, this choice of bases that I made for my cycle, it's just a choice. So it's nonsense, and it's not unique because we have as L to Z. But of course, we need to choose a basis in order to do anything in this life, yes? Yes? Okay, we are almost there. We basically have it. There is one more math fact, and then we identify the solution with a physics solution. So we are describing a torus, and we need to say what is the modulus of the torus. So by the way, what I just wrote, if you have never seen this type of thing, it should not make sense. But once I am writing because I will really write very explicitly the integrals, and when I will write hypergeometric functions integrals, you will know where we are. So it will be completely fine. It's just that now I'm telling you the math words, yes? So the math words are, so we want to know this tau of u, what it is, and the answer is when you have a auxiliary curve like that, there is a holomorphic one form, and the integral around the cycles, we have the A and the B type, we take the ratio, and this gives you this. So this is, but again, if this is not making any sense now, once you see the integrals, you will be very happy. At least this was my case when I first learned this. I was like, why? Yeah, the y is this y, yes? Y is equal to what I wrote up there. Yes? So we know this very explicitly. And now how do we identify this with physics? It's very simple. So the periods of these omega and omega dual when this u goes to infinity to our singular points. They must have the same monodromies. I mean, of course, I chose everything so that they will. This is the way to identify the solution. And the solution is this integral, but now we will write explicitly. So tau of u of the torus, the math object, is going to be equal to the IR holomorphic coupling that we are trying to calculate. This is our task in life. And we will compute it with the math formulas. Like this. But this, because of what we have, and here I am using our magical equations. Yes, it will be of this form, which will also now I will write more what these things are. Yes, so this is going to be that. Okay, we will make it. This is used, if you wish, it's identification. And why this identification is good? Because as we will see in a second, super clearly with our bare eyes, omega and omega d have the same monodromies as A and D, which is the ones that we want to find. This is what we are doing. Okay, now we write equations. Maybe I can squeeze here something simple. So you can integrate in U. Sorry, this is the absolutely last definition, but we have to say this because this is the Cyber-Witten form, which is the famous thing, so we have to say this. So what is this? So this we identify from what I have written. This is already there with the one form, which we just know it. Yes, I just write everything full on. This is just that. And this can be written, of course, up to a constant that we don't care about. So this is an integration constant. In math language, you can say that it's an exact form. Yes, so this is the famous Iberwitten. So in some sense, all they did is that they wrote the curve that I have deleted now, and they parameterized the torus like this, and then they wrote this, and then they are done. They are just doing the integrals. Yes? And let's just write now down the solution. So this is the solution of the problem now. And then we will look at it. And there is an overall normalization that one needs to fix. But of course, how did I fix it? With the weak coupling. So whatever I wrote in the weak coupling from the Coleman-Weinberg calculation, I need to get that in the nose. Yes? So then there is really nothing to worry about in this life. So this is my A cycle integral. And of course, this is what I'm matching there. To the fourth, I put these things together so that it looks smaller. Yes, thank you. Yes, please, I am writing now. Yes, please help me. Yes. Hopefully, I can only make very obvious mistakes at this stage. So this is our beautiful B-cycle integral, yes? So this is the solution to the problem. And I already wrote in some blackboards ago the definition of the hypergeometric function. And now I can also write this thing equal to the hypergeometric functions. Can I fit it here? I can, with a little bit of care. So there are some prefactors, and hopefully I did everything nicely. So I claim that this is just this. There is an I. The factors are a little bit sneaky to get right, so I got them a lot wrong until I made them nice. Whoop. So this is, okay, I go to the faraway corner and I check. This should be the correct solution, full glory. even I claim with i's and pi's and everything, and factors of 2, everything should be perfect.
Sorry, but,
Yes.
so you define A as the integral of lambda sublogarithm.
Yes.
And then lambda sublogarithm of that.
Yes.
But then where does the factor of 1 over pi come from?
The factor of 1 over pi is a choice. I said this, maybe I will write this. So there is an overall normalization, which I fix because I like it. How? So that I get on the nose, when I take this and I expand it, I get on the nose the Coleman-Weinberg calculation. The Coleman-Weinberg calculation, whatever I wrote. Bam, with no, like everything should be perfect. I's, pi's, everything. So this is the solution to the problem. And by the way, it goes without saying, if you know these two babies, you just write, yes? Tau of u equal you just write, yes? And maybe I will finish, I will write one more thing, and then if you want in the Q&A, I have done many nice calculations that I take these beautiful integrals, because we are physicists, this is what we need to learn. We can play with these integrals and really demonstrate the monodromies, really. So you should be able to take these equations and get these matrices that we wrote. This is really the real physicist, yes? So now I just write one comment and I stop. So if you take this and you do the weak coupling expansion, these are some coefficients that I'm not gonna write, but they are known. By expanding, you can take Mathematica, write this formula, ask it to expand as much as you want, and you can start writing down these numbers, yes? And, okay, this is not obvious, maybe to you now, but these are the instanton corrections. And these instantons, clearly before Seiberg-Witten curve, people have been computing, of course, pane by pane. 1 instanton, 2 instantons, okay, basically that's it. And they have been finding, numbers in front of them. And the magic of Seiberg-Witten is that they precisely with these formulas, they got the right numbers. Yes? And then, of course, Nekrasov came and did it with localization, and then he captures all the numbers. Bam. Okay, stop. Yes, please ask some questions.